So, for question number 4, we're asked, are there any values for A and B that actually make this statement true? So, right now, this looks really ugly. I know that we all aren't real fond of fractions. So, the big idea is let's get rid of these fractions. Let's start to work this through this equation and find a way to make this thing work. So find a common denominator. In this case, we've got A plus B, we've got A, and we've got B. So that's our common denominator. They have all of these three things in common. So to get rid of the fractions, we have to multiply by this entire expression. So I'm going to distribute this through to all three fractions, kind of like so. When we do this, notice that the A plus B and the A plus B will cancel here, leaving us with just AB on this side. In this fraction, 1 over A is going to make this A go away, leaving A plus B times B. 1 over B is going to make this B go away, leaving A plus B times A. When we clean it up, we're left with AB equals A plus B times B plus A plus B times A. Now we can distribute to put all this together. So we have AB equals A times B is AB plus B times B is B squared. Then we have plus A times A is A squared, and B times A is AB. Okay, now we can combine like terms. So I have an AB over here, an AB here. So I actually have two ABs. And I like to put things in alphabetical order. So I'm going to say A squared plus 2AB plus B squared. Now, the interesting thing about A squared plus 2AB plus B squared is this is actually a perfect square trinomial. And one of the giveaways for that is you got A squared, you got B squared, and you've got this 2 times something in the middle. Okay, so that format is a dead giveaway that we're dealing with a perfect square trinomial. So when we clean this up, what we actually have is AB is equal to A plus B quantity squared. Now, the question is, so what? How does that help us at all? We're trying to figure out if there are any values of A and B that make this thing work. But one detail that we've just shown here is that if these two values are equal, on this side, A plus B squared will always be positive. So that means that A times B, the product AB, must be positive. Now, the next thing I can do is go back to this line where AB equals A squared plus 2AB plus B squared and start to somehow get rid of something. Let's get rid of AB on both sides. Now we get this equal to 0. So this is something, if it did factor, we could factor it, but it doesn't. But now let's look at this statement. AB must be positive. But if this squared gives us a positive, this is positive, and this square gives us a positive, then there's no way that we would get a 0 because all three terms would be positive. So therefore, there is no value that AB could be positive. So that justifies the fact that there are no values So, one last detail to note is what if A or B were zero? Because that's worked for us before, right? Well, in this case, it can't happen because we go back to the original equation 1 over A, 1 over B, both tell us that we cannot divide by 0. So even though 0 would make this equation true, from the very beginning, A equals 0 and B equals 0 are both excluded values. And that's how we've done algebraic proof to show that there are no real values for A and B that solve this. So therefore, this cannot be a linear transform.